Okay, so we have been talking about covering, packing and this. For next few lectures, we will talk about what is called connectivity. Okay. Okay, so we know, we already have dealt with what basic connectivity means. So for now, let's focus on vertex connect. So remember, so we said that G is K vertex connected, okay, or we will just say K connected, okay. If for all x subset of Vg, mod x less than equal to K, G minus x is connected, okay. So when I say that graph is K connected, it means that if you delete any at most strictly less than K vertices, then the graph will still remain connected, okay. Okay. And second, so it is basically, this is what when people say connected, this is what they mean. And there is also G is K edge connected, and this we always say K edge connected if for all x subset of E.g. edge set is connected, okay. So this is a basic definition of vertex connectivity and edge connectivity. Strictly less than. Okay. Okay. So this is called vertex connectivity. What symbol did we use for vertex connectivity? Lambda or kappa? For vertex connectivity we use kappa, right? Kappa of G, and the edge connectivity we had lambda of G, right? So we know that kappa of G is less than equal to lambda of G, right? Because from every edge you can just delete one vertex, that will result in at least deleting this edge and something more. So this relation happens, okay. I mean, this just shows vertices are more powerful than edges in terms of deletion, and that's true, right? When you delete a vertex, you delete all the edges which are incident to it. That's it. Okay, so now we want to understand the structure of two connected graph. Okay, so what is the structure of one connected graph? What is the structure of one connected graph? G is connected, right? So then we know that we just saw that for all x subset of Vg, mod x less than equal to K, blah blah blah, G minus x is connected. So G is connected means what? It is like one connected, means you cannot delete 0 vertices and keep the graph, make the graph disconnected, which basically means what? What is the definition, alternate way of telling connectivity? That from every one pair of vertex, like from one vertex to other vertex, we can go by a path, okay. Okay. So can we prove something very similar for say two connectivity? Yeah. So what we want to show the following. Okay. So you know what two paths are internally disjoint means they have a common vertex at the end, but other vertices in these paths are they do not intersect. So this is a very famous theorem, not famous, but like it's a good theorem by Whitney. What he says is the following. Let's see if they have some. Okay, so what is the theorem? Okay, so we have three vertices. A graph G having at least 3 vertices, okay, having at least 3 vertices is two connected, if and only if for each pair u comma v in Vg, right? For each, okay. If for each pair there is two, there is a pair of internally vertex disjoint paths. Okay. Which direction is obvious? So what it tells you, the graph G is two connected if and only if you give me any pair of vertex, okay, I can find, okay, and then maybe we should also be able to prove that graph G is K connected if and only for each pair there is at least K, right? But let alone go there, let's try to prove further two connectivity. Okay. So is the statement clear? Okay. Now tell me which direction is obvious and which direction we can, like which direction is non-obvious. One direction is obvious. This implies this is obvious? No. So, okay, so what you are saying, what is obvious is, okay, graph G is two connected, okay. So G is two connected, and now I give you pair of vertex UV, you have to show me two internally vertex disjoint paths. Okay, so what you are saying is this direction is simple because there is a pair of internally vertex disjoint paths. Okay, so now we have to show that graph is two connected. Okay, so now what we have to show for all x in VG, right? G minus x is connected. Am I right? This is all that I have to show, right? Suppose it is not connected, then what happens? You have get two different connected components. Look at these two vertices, right? Now, I know that in my old graph there are two internally vertex disjoint paths between this and this. Two internally. Now, this path, one vertex can only intersect at one of these guys, no? So there is still a path, right? So this is connected. What will change if I would have replaced 2 by k? Will the backward direction happen? Right. So suppose I would have taken some x subset of Vg less than k, and suppose graph becomes disconnected, then there is a vertex u here, vertex v here. In my old graph, how many vertex disjoint, internally vertex disjoint paths I have? K. Right. Now mod x less than k, it can only hit at most k paths, so there is still 1. So reverse direction is definitely true even if we replace 2 by some number k. Is that fine? Okay. So I'm like 2 because it is slightly easier to visualize. Okay. So if for pair of vertices you have so many guys, then this is fine. Okay. Now let's try to prove the forward direction. Okay. And forward direction I am going to prove by induction on something very interesting. Induction on the shortest path length. Induction on DUV. So what I am going to say is that if the shortest path between two vertices is 1, then the property holds. Okay. Then I will say the shortest path between two pair of vertices is something, then okay. So this is going to be an induction on DUV. Okay. What is DUV? It's a shortest path, length of shortest path between u and v. Okay. So what happens if DUV is equal to 1? Okay, rather than saying induction on DUV is like length of the shortest path between a pair of vertices, like not UV is not fixed here. Okay, induction on length of the shortest path between a pair of vertices. Induction on length, no, induction. So I'm saying picks a pair of vertices. First I will take care of all the vertices which the shortest path is 1. then I will take care of all the pair of vertices whose the shortest path between them is 2, and so on and so forth. Okay? So, induction on length of shortest path. Okay? Okay? If for some pair, so this is some pair uv, duv is 1, then I want to show that this is my base case. So, first I am handling all pairs of vertices which shortest path between them is 1, which is basically a pair of vertices which are joined by an edge. Okay? Is that fine? Because I have to prove this for every pair, right? So, let me first prove it for a pair whose shortest path is 1. Okay? Okay. So, what will happen? Do we have a path? It's 2 connected. So, if I delete this edge, look, even if I delete one vertex, there is a path, right? So, if I delete an edge, right, there should still be a path. Why? Because look, lambda j is greater than or equal to kappa j.
But aren't we talking about vertex connected?
Yes, that's okay. But like I also have this property, no? So, if graph is 2 connected, it is also 2 edge connected. If graph G is 2 connected, it is also 2 edge connected. This is exactly why I wrote this. Okay? Since kappa of G is greater than or equal to 2 implies lambda of G is at least 2. Okay? Okay. Now, what happens? Now, look at G minus UV. G minus, this is not set, G minus UV. What do we know about this graph? Right? There is a path, G minus UV is connected. So, what we know? G minus UV is connected, implies there exists a path between U and V, right? And now, you go and put back your edge UV and you are done. Is that fine? So, we have so base case we have handled. So, now let us look at all those. Now, I am going to talk. So, I mean like okay. So, now we have taken care of all pairs for suppose for which duv is less than or equal to L for all such pair uv. Okay. Assume we have 2 internally vertex disjoint paths. Disjoint path. Okay? So, we have proved it. Now, let us try to prove it for all those pairs whose shortest distance is say L plus 1. Is that fine? Okay. Please ask.
So, here we are showing the forward direction, right?
Yes.
If a graph is 2 connected, then there are 2 vertex disjoint paths between any 2 pairs. So, in the induction, in the base case, for any U and V, and it is 2 connected.
G is always 2 connected.
Yeah.
G is given to you. G is fixed.
Yes. So that means from G, if you G minus in G minus X, every U and V are still connected. But here we are removing an edge, right?
Yes.
So
Why do we know this is connected?
no, I mean. Because
This is true.
2 vertex connected,
Yes.
but then we are removing an edge.
Correct.
So we are not making any change to the connectivity at all. It is still 2 connected.
Why? By maybe after deleting an edge, graph becomes. So, okay. But all I am saying to you, because even after deleting 2 vertices, even after deleting a vertex, any vertex, the graph remains connected, then it is definitely true that if you delete an edge, graph will still remain connected. That's all that I am saying. Okay. I mean if you don't like this proof, there are several ways of proving it. Okay, you take this, look at u, delete u from the graph, look at some neighbor of this, right? There is a path from here to here, there is an edge, you go to this. Is that fine? I mean, you can prove it in several ways. So I just wanted to use this simply. Otherwise, we could have also proved it directly. Delete u, okay, and you fix v here, and look at any neighbor of u. There is a path between them and them, right? You take that path, and now you concatenate with the edge wu. You have a path between uw in graph, deleting this edge ub, and that's also will do the job. Okay. So I have just used the fact that even if you if you are vertex connected with it also implies that you are that much edge connected, although the converse is not true. That's all. Okay. Okay. So now we have proved this. So now let's fix uv, right, and some. Okay. So now you fix uv and say duv is equal to L plus 1. Okay. So there is some shortest path, right, and there is some shortest path between u and v of length L plus 1. Let us fix some vertex w of d. So this is some shortest path between u and v, and this is w. And what is the property of w? duw is how much? W is the last vertex before v on this shortest path. Let this is p star is the shortest path from u to v, and what is the distance between uv is L plus 1. Then what is the distance between u and w? Right? Otherwise it cannot be shortest path, right? So this is L. Now by induction hypothesis, what do you know about u and w?
There are
two internally vertices joint path. So let's write down those two internally vertices joint path. So my role for w was only this much, to say that the distance between u and w is L, and now you see why this is happening. Okay. So let's write down P and Q. Okay. This is my two shortest path. Now what I know about some path, some internal, sorry, what I know about G minus W. Is this graph connected? Okay. So G minus W is connected, implies there exists a path in G minus W between U and V. Okay. Is the proof looks okay to you now? Okay. So let's draw that path. Let's call that path R. So that path, this is my R. Okay. If R is disjoint from either P or Q, we are done, right? If my R is disjoint from either P and Q, then you are done. I mean, I drew like this, but your structure could very well look like right, and your R, then this blue and this red is a good case. Okay. So the situation which we have to handle when this path R intersects both. Look at the last time it intersects P union Q. Okay. Let Z be the last vertex R intersects on P union Q while traversing from, okay, nobody can read this, traversing from U to V. Okay. So suppose this is my Z, then what can you say? if this is my Z, then I will take Q, I will take this and then this path, right? Okay, so okay, if this is the case, then what is my path? This is one path, right? And what is my other path? Other path is this, this and this. Okay? Okay? Without loss of generality, you can write it down explicitly. Okay? Let Z be on P without loss of generality. I mean, it could be also on the Q. Then, what is the path we will take? You take the paths are U to W via Q and W V. So, this is my one path, okay? U W via Q and this, and then other path is paths are, then you take U to Z via P and from Z to V via R. Then that is it. Because this portion does not intersect either P or either Q. So, this is, so we have shown it. But this proof, this side of the proof, can we generalize it? Can we generalize this part of the proof for K? I wrote the whole proof. I just want you to spend few minutes and tell me if each portion of the proof can be generalized. So, suppose I apply the same induction hypothesis, like will anything change in the proof? Base case holds, right? Because it is at least k minus 1 vertex k like, but you have to be careful. For 2 it was okay, but for 3 itself, what happens in the base case? Look at the difficulties which we face in the, I said k minus 1 edge connected, right? This is all that I said to say, but now those k minus 1 edge connected paths could intersect among themselves, no? Can't say anything, okay? And if I deleted this, I will get some k vertex disjoint paths here or something, or like k minus 1 vertex, but how do I, from this guy alone, can I push it, okay? But could I have not done the following? Let us just okay. So, maybe we can salvage the base case. I am not going to, I do not even know the proof. So, it is not. Suppose you have U in V, there is an edge between them, okay? And now there is a W and there is an X. And suppose we apply induction on K, right. So, maybe then we can salvage something. Let us try to understand that, right. So, there is a V. Suppose this is definitely, if I deleted one vertex, the graph, if it was K connected, this is K minus 1 connected. It means by induction hypothesis, I will have lots of paths between them. Okay. But it's between W and X. Now, even if I take this path, they will become like this. So, it becomes, you get my point, it becomes very difficult, suppose this is U, to get that many disjoint paths, because so now we have to somehow apply induction not only on this, but on its neighborhood that I have so many paths, so that I can push them separately via V like this and then try to get U. Okay. So, there are technical difficulties in just trying to push this proof for this case. Okay. So, you need to either apply induction on higher values of k first, right, and secondly you might also have to generalize it to larger objects. You understand my point? Okay. So, we understood this fact. Okay. So, this is how. Okay. So, from once we have proved this theorem, there is a very nice corollary. Okay. Corollary. If G is 2 connected, then every vertex belongs to a cycle. Is that true?
The generalization of Hubbard theorem is true. We just didn't eventually prove it.
I think it should be true. Yeah, it should be true. And but it's not that I have not. The proof is not in my head, but I know the statement is true. It should be true. That was not part of our today's course plan. Okay, but I still wanted to tell people that this statement holds, and maybe we all can try independently to boost this proof to this thing. That's all. Okay. So, is this statement fine? Okay. So, the reason why I told all this, because in graph theory or in there's something called structure theory. Okay. Now, when the graph is very connected, very connected, they have some nice properties and that could be exploited. So, you want to somehow decompose your graph into these kind of pieces. Okay. So, that is one kind of things people try to study. Secondly, people try to study how we can construct these graphs from basic blocks, like what operations can be employed that we could construct these graphs from the basic blocks. So, if I ask you, what is the most basic 2 connected graph that you can think of? Cycle. The most basic 2 connected graphs are cycle, because of our corollary that every vertex lies on a cycle. So, any 2 connected graph must contain a cycle. So, if I tell you what is the most, so look at a cycle, every vertex is 2 connected here, right, and that is the most simplest form of 2 connected. Now, we will try to prove a theorem which will try to tell us that any 2 connected graph can be constructed starting with a cycle and applying some operations to it. Okay. Is that fine? Okay. And then, so this is one property we will talk about, construction of graph. Okay. Now, not every graph can be constructed in a particular way, but then you need different kind of operations, right? And then we will learn structural decomposition versions of 2 connected graphs. Okay. So, if I ask you, how do you think we can obtain any 2 connected graph starting from a cycle? This is a cycle which is a 2 connected graph. what do you think, what operations can be employed on this? Well, we will have to prove that but what is the basic operation do you think one should be able to apply such that first of all this pair, like so what I want to do an operation in a way that this property is true, because if we are able to maintain this property at every step of our construction, then we are maintaining that, okay, the graph is two connected, I am adding something more and still maintaining the graph is two connected. Having that goal in mind and having this theorem, what operation should I do which will still maintain the graph is two connected? You got my point, right?
Adding two vertex disjoint paths is like adding a cycle.
Correct, right? But I want to maintain at each stage of our stage the graph is two connected, right? Correct. So what could you add? Because ultimately your graph is connected because it's in fact two connected, right? So rather than adding, look, if you add some other vertex uv and a cycle here to, this is a two connected graph in itself, but if I add this, these are like disjoint blocks, so we shouldn't be doing that. I want at every inductive step or every step of our construction that whatever object you have is two connected. So what can you do here?
Start with the vertex from the cycle and then follow the two internally vertex disjoint paths.
I think subdivide operation.
What do you mean by subdivide operation?
We can subdivide an edge.
Yeah, that is, you are going to get one. So if I start with a cycle, all you can construct is cycles.
Take outside a vertex and you can consider two vertices.
Okay, he says this operation. Will does this help?
The number of edges between
Huh? Wait. But does this operation maintains the properties two connected? He just took one vertex and added to the cycle. Is that fine?
the number of vertices, the number of edges between these two vertices are two large, then deleting two vertices in the middle can still keep the graph connected.
No. I'm trying to construct. I'm not trying to delete.
It is
Look. You are not. I could also have a graph like this, right? Which is two connected, right? So I'm not trying to make larger and larger graph. If I have to just make a larger graph, I can just take a larger two cycle.
our goal is to construct a large two.
No, I'm trying to construct any two connected graph. Any. So I'm just trying to see that if I start with a cycle, what all allowed operations could help us to build this object and then try to prove formally that yes, these operations suffice. Okay? So no deletion operation, only addition things are allowed. Suppose if I ask you this, you can't delete it. What all? So what he says that if I look at a cycle and add a vertex and do this, then this maintains the property that this object is two connected. Okay. So suppose, forget about this as a cycle, and I have some, this is an H. What is an H? It is a two connected graph. Okay. It may not be cycle, maybe we have constructed enough object and I just picked up one vertex and added like this. Does it maintain? Like I took one vertex, I picked one vertex outside, picked two vertices inside H and I added edges between them. Does it maintain two connectivity? Why? Suppose this is X and Y.
There were two paths from every vertex to X.
Okay. So here's my H. Okay. Two connected. Okay. Now you picked up two vertices X and Y and you added a Z like this. Okay. I want to show this is still remains two connected. How will I prove this? So that is anyway true, right? That is anyway true for two vertices A and B. There are, because H was two connected. So internally itself they have. But now you have to show to me via why this is true about a pair A comma Z.
Because we can make one path via X and another path via Y.
There is a path from A to X.
Okay, so there is a path from A to X.
And there's a path from A to Y.
But why they?
Need not be internally disjoint.
You get my point? Right? They may not be internally vertex disjoint. What else can you apply? What is like? Is this the only way to show two connectivity? Then exactly. So do that, no? So if I delete a Z, of course this is two connected, so it is connected, right? If I delete an X, okay, X, look, so look at delete any vertex, you have to show that this graph is still connected, and that is true because Z is connected to both X and Y, so you will only delete one vertex, no? And internally I can get to X and then I can get to Z, right? Right? So that's it. So it may not be necessary, it may not be that you can always apply this, but there's a simpler definition, right? So what we can show that, look, if this is how your graph is, look at for all W in H plus Z, let's call this H prime minus W is connected. Okay, that's it. So this implies that this operation is a safe operation. Can we generalize this operation? Why is only Z? What happens if I added some path P, just path P between X and Y? Will this operation not hold? You get my point? Rather than adding one vertex in this, I added a path between X and Y. With except X and Y, every vertex is outside. This is an outside. It's not a single vertex set, but like it's a path. I claim to you this is still two connected. Okay? Have you heard of this word called ear decomposition? So this is like an ear. Okay? So when you see this word, it looks so fancy, no? Ear decomposition. So this is the ear. Here's a human and this is an ear. Looks like an ear, no? If not, I can make much more like a ear. Okay? So this is it, and we can prove that this operation suffices for two connectivity. Okay? Okay. And these kind of path are called H path. Okay? What is called H path? H path are basically a path where the end vertices are in H and every other vertices is outside. So what is H path? End vertices belong to vertex set of H and all internal vertices are outside. Okay. So I have proved the forward direction, that if I apply this operation, graph remains two connected. What I have not proved upfront to you, that if graph is two connected, how can you, like, how will be you able to apply these operations? Like, how can you construct your two connected graph applying these operations, right? So, okay, so I'm saying this is good enough. So let's write down the statement of the theorem. Okay, so
Two connected means like even three connected graphs can be constructed. At any k greater than
yeah, but like, yes, you're right, but you're completely correct. Any higher connectivity graph can be constructed in this way. Any higher but like, but it doesn't tell much. You understand my point? It's like, okay, you're two highly connected that you can construct some of these things this way. There's like, all I require is the graph is two connected. So it could be 10 connected also is two connected, right? So you're correct, but why are we doing this? I will like, what is the purpose of doing this? Okay, so how people use it, lot of time this helps you in induction, like on the number of steps in the ear decomposition, because now if you're trying to apply induction, right? So how do you apply induction for connectivity? Think for a minute. You say, okay, take a tree, take the leaf out. The graph is still connected, right? Because tree was a witness of connectivity. Now if you wanted to maintain true connectivity in your inductive process, how will you go about it? It says, let's look at the year decomposition. Look at the last year. If I delete that, what is my graph? Graph is still 2 connected, and you can apply induction, right? So this is how in most proofs I have seen how the year decomposition is used. So if I wanted to prove some property about graphs, which is, but now if I wanted to prove some property about 3 connected, I would need some such kind of things, but somehow it will just degenerate after some point of time. If when it is degenerate, you come up with decomposition, which says that, okay, it's almost what I wanted, but like not exactly, and we can still make use of it. Okay. So I am trying to put seeds for the modern graph theory, okay, from where it comes. Okay, since I don't want to, okay, bundle my statement, let me, this is a theorem. A graph G is 2 connected if and only if it can be constructed, if and only if it can be constructed from a cycle by successive adding H paths to graphs H already constructed. Okay. So whatever process I did, I have just formulated it here. Okay. So which direction is obvious? This is obvious, because this is exactly how we came up with this, right? That when we do this, it keeps the property that graph is 2 connected, right? So to come up with a necessary condition, we already had a proof that, okay, look at this, if you do this, this. But now we have to show that if the graph is 2 connected, you can indeed construct this graph G using this 2 operation. Okay. How do you think we'll go about proof? Okay. So it's a graph theory. So I don't have to give you an algorithm, right? Like, I think we can come up with a construction, because once I give you proof, you can come up with a construction. Like you start with a cycle, keep adding it, and you should be able to add it all the time. Right? There is no predefined sequence. You can solve you can actually come up, it is not unique, so you can come up with in polytime. Okay. So let H be a subgraph of G, subgraph that is constructed by the above process. Okay. So what is this? Like you started with a cycle and added this. Let H, and it's a maximal subgraph. Okay, and H be a maximal such subgraph. Okay. Why such a cycle? Why such object exists? Because it's 2 connected, so it has a cycle, right? So it has a cycle C, means I can start here, no? Maybe I can't add anything anymore. That's okay. But then this is a maximal H subgraph that I can construct by this process, right? So such a subgraph, like we can start the process. That's all that I'm saying. Okay, first thing. Like you cannot extend it any further. Like after I have constructed this H, okay, I cannot find 2 vertices U and V which has a with a vertex joint paths like this. I am not able to find. That is why it's called maximal. Okay, so there is no pair of vertex U and V such that it has a path from U to V such that other vertices are external, outside. This is it. Okay, then I am going to call maximal. First of all, notice one thing. maximal such subgraph. Okay. Okay. So if h equal to g, we are done. So there is nothing. Okay. Second point is h is an induced subgraph of g. Why? Look at your h and you decided not to put an edge. This satisfies the property, no? That it is an edge between x and y is also an edge path. So you can add this, right? So if you assume that h is maximal, you better have this. So h is an induced subgraph of G. So this is a okay, excellent, right? So now what do you mean? Then what is the property? This is my h, and h is an induced subgraph of G, which implies that if h is not equal to G, there is a vertex outside, no? Correct? Okay. What I am going to show that if this graph is too connected, then I should be able to find such a path. That's all that I am trying to show. Can I show now? Think, we have done this before.
He has at least 2 neighbors in each.
Okay.
The other neighbor
Why V has 2 neighbors in H?
towards V, otherwise that
V is a vertex which is not in V of H, right? Because we agreed that H is an induced subgraph of G. So if H is not equal to G, there is a vertex V not in vertex set of H and W in vertex set of H, right? There is an edge V here, W. Like just take those as is. Okay? Okay. Base case, base case.
There exists some vertex outside.
Yes,
Such
but
that there is, or some every vertex.
no. There exists a vertex. There exists a vertex V and W such that V is not in vertex set of H, W is in vertex set of H, and VW is an edge of G. Right? This will always exist because they are connected. So pick up one. Okay. Now we are almost done. Okay. So let's do this. I could have used this proof, but like fine. Okay. So what is the property of G minus W? Excellent. So there is a path from V. So there exists a path starting at V and ending in H. H minus W actually. I don't know how that path is, but there is such a path, right? It could, okay, there is. So look at the first vertex that it ends, right? Now you put back W. What you have got? Call that X. I have got a path Wx which can, so H is not a maximal subgraph because H can be extended to something different. Is that okay? No, yes.
See, suppose there is an edge between V2, that H, another edge, just edge.
V2?
V2, that H.
Yeah.
How will you get that edge?
Meaning, I don't understand this.
In the construction, if some vertex has 3 neighbors.
I don't know how to get those edges.
So V has degree at least 2. That word we can say.
At least 2 is fine. Degree is 3.
Do you understand the proof? Or you don't understand the proof? First, let's get there.
Yeah. The contradiction comes from the maximum.
Yeah. So now what's your question? Think. Everything is there on the board. What the first step tells us? Read, no? It's there. Second. Once I added V, look at all its neighbors. There's a trivial one edge path. So, they are trivial. I mean, the problem is that one edge path is not a path. So, once a vertex goes inside, all V and all its neighbors inside this can go inside. You don't understand? You understand, Satya? Your problem, what happens if the vertex is degree 3, no? Like, did I answer your question or did I not answer your question? Then why are you saying that you understood? What happens after this I added? This is what your issue is, right? So now look at a graph which is this H, where V is included. Okay? V is inside, right? And then Y is also inside. Is this not a path, H path? Then this is exactly what I wrote here, no? H is an induced subgraph of G, if it's maximum. So if V can go, all other guys because of the one length path will go inside. Yes, please ask.
I understand this proof, but if the graph is two connected, then the minimum degree has to be at least 2.
Yeah.
Why to take this type of thing? Like, take V and take 2 edges, that is an edge path.
Why it could degree 2 could be to somewhere outside, no? I mean, you are just trying to tell me that I can construct this graph by just 2 length path all the time. That's not necessarily true.
Is there also a fast algorithm?
Did we already did a fast algorithm, no?
Because
Start with a cycle. Start with a cycle, make it an induced subgraph. Start with a cycle. Take any cycle in a graph, right? And then make it an induced subgraph. That's easy. And then you know that this proof tells us, because there was nothing about H here. Any graph will have this property. Look at the proof, no? Look at any H which is 2 connected and the graph G is 2 connected, you will always be able to find such a structure. This is exactly what the proof shows us, no? You start with any H.
here H was like assuming for contradiction.
Yeah, but suppose it is not. Okay, you start with any H which is 2 connected at every step. Okay, then tell me why this proof will not hold. You understand my question? Suppose, where did I fact that H is maximal? It was just for this, but imagine that I was applying an algorithm. What is this? Either you have reached the final stage or here's a way to add it. That's an algorithm, no? So either we are done, or if we are not done, what I have shown to you. How to extend it, no? So extend it. Pratik, either we are done here. So suppose you are not done here. Then what happens? H is an induced subgraph of G. Why? Because otherwise we could add an edge. There's a single edge, right? That's an algorithm, right? Okay. So you applied this operation as much as you can. Now you go back. Is H equal to G? It's not. Then I come here. Okay, H is not equal to G. Then what I'm saying? Okay, then pick any vertex V. I will actually find you a path like this. This is a construction, right? So in any extremal argument, you can always look at the cases which shows that it is not maximal. Is those construction polytime? If it is, then this is a polytime algorithm, right? That's it. So if H is equal to not G, so this is my algorithm. If H equal to not G, find a path, one length path. This is what this tells. Okay, if it is, so make the graph induced subgraph. Okay, is H equal to G? No. Then I will find such a path. And the proof tells us that you will always be, like such a path will always exist. That's it. So correctness will follow from this, and like why the algorithm will succeed will follow from here, but why you are, and so your algorithm will succeed, and this is a polytime algorithm.
So in the second step, we know that H is an induced subgraph because we consider the maximal subgraph.
Yes. Yes. Okay. So if I was just doing algorithm, no, I'll write this as steps of my algorithm, right? For each of this, find a pair of vertices with a path from outside, right? So, and I will give an algorithm for that, and then I have to show why it's correct. Then I will have to do this proof first. Is that fine? Okay. So I want to what are maximal two connected subgraphs? Do you know what they are called? They have a name in graph theory. They are called blocks. Okay. Let G be a graph and H be a maximal two connected subgraph. Maximal two connected. Then H is called block. So first of all, what is H? If it is maximal, what can you say? H is an induced subgraph of G. If it is a maximal two connected subgraph, then it is an induced subgraph. Okay. Right. So this is first thing to observe. If the graph was connected, whatever the connected, if I say graph, it's say, imagine the graph may not be connected, then what would its one connected pieces? Connected components. And what is the property of connected components? That they intersected at, two connected components intersect at most how many vertices? Two connected, like a connected, like I give you a graph G, I give you two connected components and they intersect at how many vertices?
The original graph is two connected.
No, graph G is connected. No, I'm not. Graph G is a graph G, and for G, I have two connected components. Zero. Okay. Okay. No, there is no two connected. Okay. So now, if I ask you, if I give you a graph G, which is two connected, okay, or may not be two connected, I don't know. Okay. But so graph may not be connected, but there are big large chunk of pieces which are connected, and they are precisely maximal. What is the maximal induced subgraph of a graph G that is connected? G may not be connected. Let G be a graph. What are the maximal subgraph of G that are connected? Connected components. Okay. So I give you a graph G and ask you, what are its maximal two connected subgraphs? So there are some H's. Okay. So G is some graph, or let's say G is connected. I'm not assuming G is two connected for now. Let's say G is connected. May not be two connected. Okay. And let's compute this maximal two connected subgraph. So first of all, H1, H2, H3, HR. Okay. These are maximal. What are they? They are maximal two connected subgraph of H. What are these? Maximal two connected subgraphs. I'm not even using the word induced subgraph, because of maximality they imply that this is an induced subgraph, but I'm not using the word. Maximal two connected subgraphs of G. Now my first question is, You understood my question? Okay. So I give you, let G be a graph and let H1 is to be maximal connected subgraph. Then you said that, oh, if I use this word for maximal connected subgraph, then their pairwise intersection is empty. But suppose graph is connected, so I start with the word. Graph is connected. It may not be two connected. And if it is two connected, how many, what is this HI? If graph G I started with is two connected, then how many maximal object will we get? Exactly one, because we can, because of this proof. Okay. So in that sense, okay. But now graph may not be two connected. So it's not that you can like get anywhere. For example, let's see one example. I give you two clicks. This is a click and single vertex. This is another, say K n and K n. This graph is connected. It's definitely not two connected, right? Because if I delete this vertex, I will get what are its two connect, maximal two connected components. So this is one, right? And this is another one. You just check. So they could intersect first of all.
So they cannot intersect on more than two vertices. They can intersect more than two, yeah.
So there, or rather their intersection is upper bounded by 1. Can we prove this?
If they intersect at least two vertices, then we can take the union and take a larger maximum.
Proof. I mean, like, I understand what will we get, but like, why? Okay. So we have a claim. Everybody has made this. So you understood what? Okay. So here's our claim, and these maximal two connected subgraphs are called blocks. So let me use the word blocks. Otherwise, like, okay. So here's my lemma. Let G be a, actually I don't even need connectivity. I was just like, let G be a graph, okay. Then any two blocks B1 and B2, vertex set of B1 intersection vertex set of B2 is upper bounded by 1. Proof.
Say the intersection has two vertices x and y.
Yes.
We know that in the block B1, moving x1 doesn't makes it disconnected. So we only have to show there are for every pair of vertices which is except xy, take a vertex as a v which is in B1 and w which is in B2, they have two disjoint ones.
I mean, if you want to make your life difficult, please make your life difficult. But there are much more easier. It- you have to just show that look at B1 union B2, okay? And because then it will tell us that this is not a max, we cannot extend it, right? So look at this, as you say, look at delete x. This graph is still connected, right? Like, okay, look at delete x. I can go to anywhere to y, and then I can go to anywhere in this, right? Similarly, if you delete y, the same happens. If you delete this, then you can still, any vertex can reach here. And so basically, that's how, right? So it contradicts the find that it's a block. So they can only intersect at one vertex. Excellent. So let's try to make, okay. So this is like a, so there are some.
So if G is connected, then this will be exactly 1.
No. Why? This block and this block intersection is empty. Okay. So it can be 0. For every block, the intersection is at most 1. Okay. So here is my first so-called decomposition. Okay. These are called block decomposition. So how do we construct block decomposition? Okay. In decomposition, now you will see why decompositions and trees are related to each other. Okay. What are some other blocks? What are the blocks here? So the blocks here are, remember, right? This is a block. It can't pick up this edge xy, because if you delete any vertex here, then you are dead. So you can't contain both x and y. Okay. So what are the blocks? This is also a block. This is also a block. An edge is a, like here a bridge is a block. A bridge, not an edge. A bridge is a block in itself.
This kind of decomposition is unique.
Huh?
This is unique.
It will be unique. Okay? But we have still not made a decomposition yet. Okay? So we'll make one. Okay? But like I just wanted to tell that generally people think about block, then only think about these non-trivial objects, but there are also some simpler blocks like bridge. Okay. So this is why in my older theorem I was writing n at least 3 and those kind of things. Remember, number of vertices at least large, then only those disjoint paths and those kind of relation. But there are, if we degrade up, because now we have to decompose my graph, so I have to also give some definition to things which are not non-trivial, but like slightly simpler, trivial. Singletons. A cut vertex is a block in itself. Okay? So blocks, okay, let's see what does okay. So how do we construct this graph? It's very nice. Okay. So we make a bipartite graph. So we have a bipartite graph here. So what is my bipartite graph? Here I write down basically they are blocks. Okay. These are blocks. Okay. They are like vertex sets of blocks. Okay. Okay. And here is like cut vertices. What are these? Cut vertices. Okay, these are cut vertices. Now, if this block contains this vertex, then I put an edge between them. You get my point? So this is like, think of this way, that this is like a blocks, and these are like there's a vertex for every block. Okay, there's a vertex for each block. Okay, and this is set of cut vertices of my graph. Cut vertices, if I delete, the graph becomes disconnected. Now, if this block contains this cut vertex, now this is a block that contains this cut vertex, right? Look, this is a cut vertex of the graph. It's just that in this induced subgraph, it is not a cut vertex. But a cut vertex could belong to a block. You get my point? A cut vertex could be a cut vertex in the original graph, right? But in the block, it is not a cut vertex. By deleting this, you cannot disconnect this piece, but you can definitely disconnect the whole graph. You get my point? So these guys could contain cut vertices of the graph. Okay. So this is it. I give an edge. So and a block can contain several cut vertices. Do you see that? Here's my click. Right? So it could contain several cut vertices. Okay? Okay. So this is my graph. Okay? You know what is this graph is? So what did I made? Block and cut vertices. Okay? And this is a bipartite graph. So there is a vertex for each block. So how do I put edge? There is an edge between block. So suppose we have blocks B1, B2, BL, and we have vertex V1 to VL here. Okay? So now you edge Vi and some C, there is an edge if and only if Bi contains C. Let's assume that G is connected for now. Okay? Then it will make, suppose G is connected. Okay? Now I made this bipartite graph, right? What is this bipartite graph? Okay? Here's a claim which we'll prove next class. But I want you to think a little bit is this graph is a tree. It's obvious if you realize we proved just now that their intersection is at most 1, but okay. Bipartite graph corresponding to block and cut vertices is a tree if G is connected. Okay? And that will tell you the interesting property. So what happens? Now I have a tree. So these blocks are like building blocks. So think of this way, what happens now. And why this is true is because of this property. How can you have a cycle here? Okay, tree connectivity is a different thing, but why? That is very easy to see. I have what is a cycle here will correspond to? Suppose this is a cycle. There's a block which this vertex is common to these guys, right? Then there's some other vertex which is common to some other guy, and there's some guy which is common to like this. But then you will start getting some funky thing here. So that kind of things cannot happen. Now, so basically what happens is that you get a tree structure, okay, and each vertex will either correspond to a cut vertex or a block. Okay. Now you can start doing dynamic programming algorithm on this, because look at this cut vertex, right? The intersection to the world below is via the single vertex. So amount of information that comes from below is via the single vertex, right? You understand my point, right? Imagine that I have a cut vertex in a graph. Okay. For example, if I wanted to, if someone gave you a very good example, so here's a property. What is a property? That you give me any induced subgraph of your graph, there's a cut vertex which is balanced. You know what is the meaning of that? What I mean is that you give me vertex set of the graph. What is the property of a graph? That you will find me a vertex which is a cut vertex, and both sides has roughly half the vertices. Can you solve maximum independent set on this graph? Very simple. You decide whether this vertex goes into the solution or not goes into the solution, right? And then recursively solve this problem. No, you have done the problem in half, right? So your T of n will become some n to the power big, like if this is single vertex, so 2 times you have made some choices, right? Either this goes into the solution or not goes into the solution, times T of another 2 times, say 2 of n by 2. It's Pauli time. So this is why we like this kind of graph, right? But this may not be true, but here I'm assuming the fact that you give me any induced subgraph of my graph, you should give me a cut vertex so that it is balanced. So when I apply recursively to the left hand side, still if this property holds, then I can still do it. So this is why these are the graphs which, there are graphs which you can construct by this separator, this separator, this separator, like which separates my graph into two equally good part. Example trees, they are very useful for algorithm as well as for structural decomposition. So prove, here's a statement for you, try. In a tree, there exists a vertex such that if you delete it, every connected component of the tree contains at most half the vertices. You get my statement? In tree, there exists a vertex, if you delete it, look at the subtrees, if you will get, no subtree has size more than n by 2. Okay. So there is some exercise. We will deal with them in algorithms, but they all are related to each other. They are also used very much structurally. Okay? Okay. So at least I'm done for the day. And then next time we will flush up some of these things and move on.